Please take it away.
Okay, well, thanks very much for the invitation to speak in this venue. Of course, I'd much rather be there in Chicago, but it's a long trip, so I'll take advantage of the technology and tell you long distance something about what Itamar Shamir and I have been working on over the last couple of years. It sounds a little bit like a dry subject, but I don't think it is really. And I thought I'd begin with a little bit of motivation of how I got into this subject and why I think it's kind of important. I'm trying out a sort of hybrid version of this seminar here, where at some point it will go into more of a Blackboard mode to try and make it a little bit more interactive. And since we have such a small group, and please just stop me at any time and ask lots of questions, and I think it will be more enjoyable for everyone. So let's see. I usually show these four pictures in these talks, and it's my nutshell version of why I think boundaries and defects are very important in quantum field theory and gravity more generally, and sort of why I've gone down this road that, looking back over the last 20 or 30 years, I see a lot of the progress in theoretical physics have been kind of tied up in this notion of boundaries and defects. And so here in the upper left-hand corner, I have my idealized picture of D-branes, which are maybe the quintessential defects, not just in a quantum field theory context, but in some quantum theory of gravity as well, which have played this enormous role going back again, to the 90s in the superstring revolutions. I have my idealized picture here in the down center of ADS-CFT, which provides this map between gravity and field theory, and where again a boundary is playing this really important role. It's a boundary now of anti-de Sitter space. As many of us know, that's where the field theory that's secretly dual to this theory of gravity lives. So again, boundaries are playing this really critically important role. And the top here, I have my schematic diagram of topological insulators. This is showing the density of states for the electrons in these materials. And you see typically they're gapped, right? They're insulators in the bulk. But on the boundaries, they have these protected surface states. They're protected typically by some discrete symmetry. And these states are massless. And again, it's the boundary that's somehow playing the critically important role in the development of the subject. And then finally, in the lower right, this is my idealized picture of, quantum information or quantum entanglement, which is actually how I wandered my way into this subject. So the idea here, right, is in a field theory context, if you want to talk about entanglement, one nice way of doing that is to separate your field theory up into spatial regions. So I have my spatial region A and my spatial region B. And I want to know the quantum entanglement between the degrees of freedom, maybe in the ground state, maybe in some excited state between these two regions. And what winds up happening is you wind up focusing a lot of your attention on what's happening right at that boundary. These entanglement entropies are typically divergent, UV divergent. They're driven by the short distance physics that happens near the boundary. And one nice way of calculating these entanglement entropies is to talk about twist defects in quantum field theory. So again, four huge subjects in theoretical physics in the last 20 or 30 years, and they all in some fashion or another have something to do with defects and boundaries. Now, my personal path into the subject was driven largely by entanglement entropy. I spent a lot of time writing papers about how to calculate the entanglement of free scalar fields or free fermionic fields at non-zero temperature, at zero temperature, et cetera. And I realized in the process of doing this that a lot of the most important results that I cared about seemed to be really secretly about defects in quantum field theory. Codimension 2, because they're it's spatial entanglement. They don't persist in time, and so these are they have a normal direction in time and a normal direction in space. And so by calculating, using the replica trick to calculate these entanglement entropies, you're really I think you're really somehow learning something more about defect QFT than really about entanglement. And so I took a step back and started thinking more about defect and boundary quantum field theory, and then conformal field theory in particular, where a lot of the strong results can be stated because of the extra symmetries present in conformal field theory. But then there are broader reasons to think about this too. There are clear experimental reasons to think about boundaries and defects. There are measurable surface critical exponents you can get by looking at these kinds of theories. You can also begin to ask very interesting questions about transport in these systems that maybe are not exactly graphene, but that are very close to graphene. And I know, for example, Dam Sun in the audience has written very interesting papers about exactly these kinds of subjects, which also drew me yet deeper into this question of boundary and defect conformal field theory. And then there's sort of formal aspects, which is really what's behind the current talk and the current two papers that Itamar and I wrote that I'm going to talk about today, where I'm going to focus on this notion of anomaly coefficients in boundary and defect conformal field theories as maybe a way of kind of mapping out the space of these quantum field theories. So that's my background motivation. And again, if there are any questions, please ask, because I think often the questions are more interesting than anything I have to say. And of course, I've heard it all before, so I'm here to listen to your questions more than to listen to my own voice. Are there any questions? No. Okay, I'll keep going then. But please, jump in and ask. So a little bit of background about what exactly I want to talk about today. I want to talk about the notion of a Euclidean conformal field theory. So time will just be like other spatial dimensions. We'll be in, we'll start in D dimensions, but then we'll specialize as we go forward. And what do I mean by a Euclidean conformal field theory? I mean something that has, well, it has the SOD rotation group, rotations in D dimensions, but then it gets enhanced to this SOD plus 1, 1. You get these special conformal transformations and dilatations that are part of the symmetry group of these field theories. And I'm going to specialize to conformal field theories which have defects or boundaries. And I have in mind if it's a boundary, it's a real physical boundary which just has one normal direction, but maybe it's a line defect or a surface defect which have larger number of normal directions, so they have larger codimension. And the presence of that defect will break your SOD plus 1, 1 symmetry down to the conformal symmetry group of that defect, that p-dimensional defect. And then there could be a transverse rotational group around the defect as well, if p is small enough compared to d. So a defect conformal field theory is something which has the symmetry group, and maybe the defect could be planar, maybe it could be spherical, although for the purposes of today's talk, just think of that as a planar or some kind of line surface defect. And now I want to think further about these defect or boundary conformal field theories as special cases of quantum field theories in some curved space. They're not necessarily just flat theories in a flat space, but in some curved space where the metric is you can think about it as an external field, an external source. And so that I recover this conformal symmetry in the flat limit, I want to have some Weil scaling symmetry with respect to the metric. I want to be able to rescale the metric by some local function sigma, and find the same theory in curved space again. And there will be an infinitesimal version of this Weil scaling, which is just given by delta G is 2 sigma G. So I realize this may be old hat to most of you, but just to fix notation and so forth, it's probably worthwhile to say these things. And I want to focus on this notion of anomalies. So, we have the definition of the stress tensor, which we can think of as the variation of the response of the action to a variation in the metric. And now, if I have this Weil symmetry, so if I change the metric with respect to this small amount with respect to the scaling function sigma, and I plug this in here, then I see that classically I should find that the stress tensor is traceless. But as many of us know, that's not true at the quantum level, that in a curved space, there's often some kind of anomaly in these theories. And the anomaly schematically can be written in this form, that the trace of the stress tensor is given by some sum over polynomials in the curvature with some coefficients Ci, which are these anomaly coefficients that are going to play a very prominent role in today's talk. And in fact, there's one particular coefficient I want to focus on for the rest of the talk, and one particular polynomial in the curvatures. So that polynomial in the curvatures, that's the Euler density. That's the polynomial which integrates up to the Euler characteristic on the manifold. And that coefficient, the coefficient of that Euler density, we'll call A sub d, at least for the next few minutes. That's historically a common name for it, or in the literature. And because the Euler density is an even polynomial, has even degree, it has degree d. Sorry, you have to construct it out of the Ricci, out of the Riemann and Ricci scalar curvature, so it has weight 2. And this whole thing has to have weight d. And so you only find this thing in even dimensions, right? So this anomaly is typically only present in even dimensional conformal field theories. Now what happens with a boundary or defect is something more interesting happens. You get to write an Euler density that's associated with that boundary or defect. So in curved space, it could be a sphere or some other funny shaped boundary or defect. And so it could have an Euler density if it's an even dimensional defect or boundary. And it could have its own coefficient, which I'm going to call A hat sub p. And now this anomaly can be present even when the bulk dimension is odd. Okay, it requires an even dimension for the defect, but the bulk dimension can be odd. And so you find this Euler density coefficient in defect and conformal field theories in a sort of slightly more general context. So why do we care about these two numbers? Why do we care about these two numbers? Well, they're very interesting, at least to me. They obey several very nice properties. One of which is that they kind of map out the space of these boundary and defect conformal field theories under renormalization group flow. And why do they do that? Well, we know in the bulk, we can think about these conformal field theories as fixed points of the renormalization group. And we know that if we have some UV fixed point, A at that UV fixed point has to be greater than A for the corresponding IR fixed point. That's a theorem that was proved in the two-dimensional case by Zemlyalikov back in the 80s. It was then conjectured by Cardy to hold more generally. And Komart-Godsky and Schwimmer gave us a proof of the case in 4D only about a decade ago. And so that's one very nice thing, that this coefficient A orders defect and boundary conformal, well, it orders conformal field theories under the normalization group. And there's another fact about these coefficients, which is maybe slightly less known, is that they're independent of marginal deformation. So here I'm seeding my RG flow with an operator of dimension delta, which is relevant because it's less than the bulk spacetime dimension. So you'll flow then if you add such an operator, hopefully from some interesting UV fixed point to some interesting IR fixed point. But if the dimension D is equal, the dimension of the operator is equal to the spacetime dimension, that's a marginal operator. So you might have some conformal manifold, some space of these conformal field theories, parameterized by the coupling with which you add this marginal operator. But then it turns out this A can't possibly depend on that marginal parameter. One way of seeing that is a property called Wess-Zumino consistency, which I'll get to in a few slides. And this statement extends to the defect case. So we can talk about the conformal anomaly for the Euler density that's associated with a defect. And again, we have proofs that A UV is greater than AIR. This was proved at least for P equals 2 by Jensen and O'Bannon just about 4 or 5 years ago. So if you seed now some renormalization group flow with an operator on the boundary, that's what this hat means. It means we're on the boundary. Such that it's relevant, so the dimension of that operator has to be less than the dimension of the defect, which in this case is P. So you seed some boundary renormalization group flow, then you get this ordering of boundary and defect conformal field theories as well. And now it turns out that this A hat P is also expected to be independent of marginal deformations, but now these are marginal deformations which live on the boundary. Okay, so that's the background. And I can finally get now to say what this talk is about. Our results. So our results, it's about what happens to this boundary anomaly coefficient when we add not a boundary operator, but a bulk operator, okay, that's marginal. So on the previous slide, this O had a hat on it, which indicated it was an operator that lived on the boundary or defect. But here I'm adding it to the bulk, the d-dimensional space, and I want to know what happens to A hat. And the claim is the following, and after which you can, I guess, leave. This is the punchline of the talk in some sense that, let me first change notation. So I had A hat sub P, which was the coefficient of the boundary anomaly. And ever after in this talk, it will be called F. And I had this coefficient lambda, which ever after I'm going to give a superscript I so that I could have some possible space of these marginal deformations, not just one. And the claim of this work is that the derivative of this anomaly coefficient with respect to the marginal parameter is given by the 1-point function for these marginal operators. Okay, so in a boundary or defect conformal field theory, you may be used to the statement that 1-point operators should vanish in conformal field theories. That's true, but here we have a boundary or defect, and in that case, the 1-point functions don't vanish. They can fall off with a power law as you move away from the boundary or defect. So R here is the distance from the boundary or defect, and they just fall off as R to the D with some coefficient, and that coefficient is what's given by this derivative. Okay, so that's the claim for the talk. That's the result of the talk. And in what follows, I'll give you lots of detail about the case of surface defects. I'll tell you a little bit about the case of 4-dimensional defects and some sense of what happens more generally. Okay.
Do these
I think I really should
values always have the same sign?
The expectation values for the 1-point functions.
Yeah.
Well, that's an interesting question. They don't. So I guess the simplest case to think about is a free scalar field. So phi, and you could ask about the 1-point function of phi squared in a boundary theory. And it turns out to be basically plus or minus n over, what is this going to be, r squared, I guess, in 4 dimensions. Where that plus or minus is whether you're in Dirichlet or Neumann, whether the scalar has Dirichlet or Neumann boundary conditions. So no.
And Fi itself can depend on lambda, right?
Yes, absolutely. Fi will in general depend on lambda, I believe. Yeah. It could be, I think, yeah, yeah. Anything else?
So here, just to make sure I understand, so here the A that is usually that usually doesn't change. Okay, yeah. So here you're saying that this quantity A that usually doesn't change when you don't have a boundary, here will change when you have.
No, it's A hat.
Okay, no, sorry.
It's the boundary
okay,
A.
okay.
That's just changing in response to bulk.
Yeah, the bulk A, I don't know how to, that won't change. The bulk A, the A without the hat won't change with respect to marginal deformations, but the boundary one, which is independent of boundary marginal deformations, will depend on bulk marginal deformations. All clear? Should I go on? I guess I should go on. So I wanted to kind of go into hybrid mode here and show you why you should expect this relation. We'll just do a short calculation to give you a sense, and we'll keep it as simple as I can. So we'll deal with a 2-dimensional boundary or surface and a 3-dimensional bulk. And because of the magic of conformal field theories, I'm free to work not just on flat space, but on hemisphere by appropriately chosen Weil transformation. So this is my hemisphere, and there'll be a boundary of the hemisphere, which is an S2. And some angle, polar angle, which tells me where on the hemisphere I am. So on the hemisphere, I expect a 1-point function for a marginal operator O to fall off as a power of the distance from the boundary, but the power here, because of the fact that I've done the Weyl rescaling, is going to go as cosine cubed theta rather than r cubed. Okay, and it has to be 3 because I'm in 3 dimensions, and that's the dimension of a marginal operator in 3 dimensions. Okay, so I'm going to do 2 sides, and do the left side and the right side, and I guess I'm starting with the right-hand side. I think so. Let W be the free energy. So if I have some partition function, my W is something like e to the minus W. And I want to think about what happens now when I change my action by adding this marginal deformation. So I'm adding d3x lambda I OI. So if I add that to my action, I can see, I think relatively straightforwardly, that if I take a derivative now with respect to lambda I of the free energy, that will just pull down the 1-point function, the integrated 1-point function, into the path integral. And so I can write this as integral over HS3 of d3x OI. Okay, so that's how the free energy will change with respect to a change in the marginal parameter. And this integral I can do pretty much in real time, right? So I can pull out a factor of the volume of the S2, and then I can do the theta integral for you, which is something like sine squared theta. That's the measure factor on the sphere over cosine cubed theta. That's the fall off of the 1-point function. I have my coefficient Fi, and I have a d theta. And then you notice immediately there's a problem at theta equals pi over 2. This thing is divergent because cosine goes to 0. So let's cut it off. Instead of integrating to pi over 2, let's go to pi over 2 minus delta. And now I'll cheat a little bit, but you can do this. It takes 2 minutes. You can isolate then a log term in this integral. There's a log term in this integral which goes as 2 pi Fi times log of delta. And that log term is going to give the scale dependence that I'm after. Right? So I could, for example, instead of thinking about a distance cutoff, I can think about an energy cutoff, and there'll be a minus sign between them. So lambda, I want to think about as some energy scale. And so I guess I haven't left myself quite enough room here, but let's go on to the next page and write the scale dependence of that derivative. So I'm going to write lambda d lambda of dw d marginal coupling, and this is going to be minus 2 pi Fi, right? Just from taking that logarithmic derivative and adding in the minus sign. Okay, so that's one side and that tells me the scale dependence of the 1-point function, if you will. And I can compare this with the stress tensor computation. So we'll compare with the stress tensor. In the anomaly in the stress tensor, the Euler density contribution to that, well, the Euler density on a 2-dimensional manifold is just the Ricci scalar. And then the coefficient we're now calling F, and I've added in a factor of 4 to make everything work out work out nicely. And I need to make sure I'm on that boundary. So this is the Euler density anomaly associated with the S2, not the ambient one, which wouldn't exist anyway because I'm in odd dimensions. Okay, so if that's the stress tensor, well, because of that, I can think about that in terms of a scale dependence of the free energy is coming. So the scale dependence of the free energy should then be what? It should be that stress tensor integrated over the hemisphere, or actually in this case, just the S2 because it localizes on the S2. So an integral d2x of r. And I'll just recall that r equals 2 for a unit S2. And so what do I get here? I get minus f over 4. I get the surface area of a 2-sphere, and I get a 2 from the Ricci scalar. And so at the end of the day, I get minus 2 pi f. And so what I learn from this is, comparing now this result with this result, I learn what I was hoping to show, that this di of f is equal to fi. Okay, if I take a derivative of this f with respect to lambda, this marginal parameter, I get the coefficient of the one-point function. Okay, so I hope that gives you some sense of where that claim comes from. And now let's take a step back and think about, unless there are questions. Okay, so let's take a step back and think about what that means more generally. So I looked very specifically at the 2-3 case, two-dimensional boundary, three-dimensional bulk. But you can do this calculation in general. There's nothing to stop you from doing it for a SP defect or boundary inside some SD dimensional sphere, which is what this first bullet point is saying. And the log, the fact that we saw a log, it's only going to show up, it turns out, for even dimensional P. So for odd dimensions, what typically happens is you'll get some constant term, which is RG independent or independent of your regulator. And there's this other story that starts that I'm not really going to talk about today about monotonicity of the sphere free energies under a normalization group flow. And there's been a whole interesting literature about that. But okay, but that's another part of the story you could go, another road you could take at this point. And so that's sort of the larger picture that follows from this calculation. And now I want to drill down on this a little bit and see what's really going on here. Is there more information we can learn about how this anomaly then filters down into other kinds of correlation functions besides just the one-point function? Is there some way we can think about an anomaly effective action or an anomaly portion of the action that can tell us about how this anomaly shows up in correlation functions more generally? And so that's going to be the rest of the talk. All right. So what do I have in mind? So let's go back to two-dimensional conformal field theory, which I think probably most of the audience is very comfortable with. So in that case, there's this central charge C, which I've rechristened A or F in this talk, but it's the same object. And one way of thinking about that, that central charge C is as some scale dependence of an effective action that comes and multiplies the Euler density terms, this Ricci scalar in a two-dimensional CFT in some curved background. And there are these very nice discussions of this in various textbooks. I guess my favorite discussion is probably in Polchinski chapter 3, where he talks about how you can integrate this up to this R inverse box R action. You can undo the variation and see how it kind of filters down and tells you about the stress tensor two-point functions. Okay, so we have this in two-dimensional CFT, and one way of seeing why this is the only thing that can be written down is this notion of Wess-Zumino consistency, that we can think about scale variations in these conformal field theories as being part of an abelian group. And so if I do two of them, it shouldn't matter which order I do them in, I should get the same result. And so this commutator of these two scale variations should vanish. Okay, so if I apply that to this effective action, well, if I take a scale variation of the Ricci scalar, it's this well-known fact, I get a Laplacian of this Weyl function. And I could then integrate up the box by parts, and I could see how it would act symmetrically on the two sigmas, the sigma 1 and the sigma 2. So it would then therefore satisfy Wess-Zumino consistency. However, if this C were a function of marginal parameters, which I could then promote to local fields, there's clearly going to be a problem when I try to do that integration by parts, because now the derivative could act on the C function instead of the other delta sigma, and I won't satisfy Wess-Zumino consistency. I won't have this notion of Weyl transformations won't form an abelian group. And you could try to fix this up, but there's really nothing you can do. You could add, for example, you could try to add a Laplacian acting on lambda, but Laplacian, the two-dimensional Laplacian is violin invariant on its own, so that's not going to help you. And so that's one of the arguments people, I think it is the argument perhaps people have put forward to say that the central charge must be independent of marginal parameters. All right, so that's the 2D story. But now when you add a bulk, things get much more interesting. So we still want to apply this Wess-Zumino consistency condition. And there's still no dimensional couplings. It's still a conformal field theory. So I still have to construct this anomaly out of objects that are weight P, the same dimension as the stress tensor. But now I have these two new objects. I have an extrinsic curvature I can play with, and I have a normal derivative I can play with. And so there wind up being 4 weight 2 objects in general I can assemble. And indeed, now I can satisfy Wess-Zumino consistency. I can form an anomaly effective action out of these new pieces. And it has this general form where I have a piece that has these 2 normal derivatives acting on lambda. I have a piece that depends on the extrinsic curvature and the old Euler density anomaly that we started with. And this was, I guess, one of the central results of our paper Itamar and I wrote about 2 years ago. So there's some flexibility in the construction here. I mean, as I was saying before, the 2-dimensional Laplacian is Wess-Zumino consistent on its own, so you could add that to this. Or you could maybe trade some of these terms for the 3-dimensional bulk Laplacian, which isn't Wess-Zumino consistent, but you could rewrite it in terms of other data here. So it's not a unique procedure, but its consequences on correlation functions should nevertheless be unique. And the last thing I'd like to say is that this is written in the 2D, 3D case, but it's relatively trivial to extend it to higher codimension. You could have a surface defect in 4 dimensions, 5 dimensions, 6 dimensions. All you have to do is add some indices to the normal vector, because now there's more than one normal direction, and an index to the extrinsic curvature, because now there's, again, more than one of them. All right. So I thought I'd again maybe switch to hybrid mode here and show you a little bit more about why this anomaly, effective anomaly action works. This is a much shorter computation. I want to show you why this first term has to be here, why there has to be this second derivative of the marginal coupling. So before I begin, are there any questions? It's been very quiet. All right, so the way to see this, I think, is to realize that there's an anomaly in the 1-point function. So let's again go to the 3-dimensional case. So I can write OI now in flat space as Fi over Z cubed, where Z is the distance to the boundary. And I'll use differential regularization to see this scale dependence. I'll write this in the form Fi over 2, third derivative of the log of lambda times Z, lambda times Z, and then a theta function, because I'm thinking about this as a boundary, so I'm living on one side of the Z coordinate. This is only present for positive Z, right? So, okay, so we can talk about scale dependence of this now that I've introduced this scale through this differential regularization. This is a procedure I think that was maybe first popularized in a paper a long time ago by Friedman, Johnson, and Latour. So if I take this logarithmic derivative with respect to energy scale, you can see what happens, right? I take a derivative, I get 1 over Z from the logarithm, and well, let's keep sorry, I take a logarithmic derivative, sorry, I take this logarithmic derivative and I basically just get a constant, right? And then I take a further derivative of the theta function. And so what I'm left with is a Dirac delta function of z with two derivatives. And I'm going through this to show you how you get these two derivatives, right? You can sort of see how this is the flat space limit of what we've written up at the top minus fi over 2, these two normal derivatives, d mu d nu of lambda I, right? Because if I take I vary this anomaly effective action with respect to the marginal parameter, I get this Dirac delta function. So you can sort of see exactly where I get this this second normal, or these two normal derivatives acting, and how that's compatible with the one-point function of these boundary conformal field theories. All right, so this is all a little bit of an old story. That's what we did about 2 or 3 years ago. And then we had in mind to kind of really put this on a firmer foundation, to look at what happens in higher dimension, to look at further consequences of slightly more complicated correlation functions. And we got stuck for a long time looking at this particular correlation function, the correlation function of the stress tensor and a marginal operator. There are a couple of other pieces of this that we were able to deal with very straightforwardly, which I'll show you a little bit more detail as we go on. One was the correlation function of the displacement operator with the marginal operator, and the other was the four-dimensional case. So those were the new results in the recent paper that we put out just a few months ago. So let me tell you a little bit more about these results, unless again there are questions. All right, so the displacement operator, I think I should probably say a little bit about what this object is. So it's a distinguished operator that's present in all of these defect and boundary conformal field theories. I'll give you 3 equivalent definitions. One is the operator that's dual to the position of the boundary or defect. So you vary the action with respect to the position of the defect, and the response of the system is this displacement operator. Another is through a word identity. So if I put in this defect or boundary, I'm going to break translation invariance. And so I expect to have some failure of conservation of the stress tensor. And that failure is measured by the displacement operator. So in almost everywhere the displacement, the stress tensor is conserved, but on the defect, because I've broken translations normal to the boundary, I'll get some response, which is also the displacement operator. It's the same operator. And then in the boundary case, there's one last nice definition. You can do a sort of Gaussian pillbox type argument, the same argument you did in your E&M class for figuring out the electric field around capacitor plates. And you'll find out that in the normal, in the boundary limit, the normal component of the stress tensor is again the displacement operator. So it's a distinguished operator that's present in all of these boundary and defect conformal field theories. So what happens, how can we expect this anomaly to show up in these two correlation functions? Well, they turn out to be very highly constrained by the symmetry. So in the case of the displacement operator, this 2-point function is fixed up to a number. It looks like 2 scalars in a conformal field theory, which we know again are fixed up to a single number. And then a kind of surprise, which is very special to this codimension 1 situation, is that the stress tensor marginal operator correlation function is also fixed up to a single number. In this case, the number of this, I'm calling it CTI. And there's some other things that show up here. There's a cross ratio V, which is written down at the bottom of the slide. So already for 2-point functions in boundary conformal field theory, there's an invariant cross ratio that can show up. And you can have functions of cross ratios that show up in these 2-point functions. But for some reason, this stress tensor object doesn't depend on an arbitrary function. It's fixed up to a number. And then there's some tensor structure that is important as well in writing down this correlation function. Okay, so that's fixed by conformal symmetry. And then you can look a little bit more detail at these word identities, and you'll see,
Chris,
for
can you
example,
just say
the
one word?
CPI.
Can you just say one
Yeah.
word about why there isn't an arbitrary function there? Just give us a hint about why that is.
Yeah, I had a good reason a few days ago.
Would it be different if it was not a boundary, if it was a different dimension, codimension situation?
Yeah, in higher codimension, it's much, much worse. So in higher codimension, you have two cross ratios, and there are many tensor structures that show up. And so you
But is it
have to
still
have several
fixed? Is it still fixed, or is there no?
As far as I know, it's not fixed. So I think it has something to do with the fact that the boundary limit of the stress tensor is the displacement operator. So you can, if you do you can do this sort of boundary conformal block decomposition. And another way of saying it, I'm not sure I'm really explaining anything, is that only the displacement block contributes to this 2-point function. So there's something special about boundary conformal field theories. It's a little bit miraculous. I didn't realize how miraculous it was the first time I saw it. I mean, it's given in McCavity and Osborne's paper from back in 1995, and I sort of learned that before I learned that 2-point functions could depend on cross ratios. So I learned it in the wrong order to understand why it was interesting. But yeah, I think it's quite interesting. Anyway, it's fixed up to a number, and because of these word identities and these boundary limits, it's further fixed up to the coefficient of the 1-point function. So all these numbers, the CDI, the CTI, they're all fixed by the 1-point function for that marginal operator Fi.
For non-marginal operators, it's not fixed. Is that the distinction you're making? If O is not fixed?
I'm just emphasizing marginal operators because that's going to be the point of this talk. Actually, in general, what happens is these, yeah, they're still fixed up to the 1-point function of whatever that operator is. It could be marginal, irrelevant, or irrelevant, whatever you like.
Okay, so this formula is general. This TOI would also hold for non-marginal up to the dimension.
I think this one needs modification. I don't think the dimensions work out quite right if it's not marginal, but morally it's true.
Yeah. So in the case of the free scalar that you briefly talked about earlier, there you explained that different boundary conditions would change the 1-point function. Here, how would boundary conditions? So here is something similar happens. Different boundary conditions would change the CTI.
Absolutely, that's a good observation. Yeah. So if you were to set this OI or replace it with phi squared that I had before, I said before there was a coefficient n plus or minus n, which was plus for Neumann, minus for Dirichlet.
Yeah.
And so again, if you were to look at d phi squared or t mu nu phi squared, then the CDI and CTI coefficients would be plus or minus depending on the boundary.
Oh, it's the same. Okay, I see. It's the same. It's still the 1-point function. It's the same coefficient. You're saying. Yeah.
Okay. I think the 6s and the pi's and the 9s may change around a bit. Yeah, the dimension of the operator figures into those expressions more generally, but morally it's true.
Okay.
There's only 1 degree of freedom in these expressions, which is the 1-point function of O.
Mm-hmm. Got it. Thanks. Okay,
so because they all depend on F, all these 2-point functions depend on this Fi, we ought to be able to see it from the anomaly action. And I can show you DO. I won't succeed in showing you the stress tensor scalar one. That's too complicated. But the DO, I think, is fairly easy to do, at least to sketch how it would work. You write it down. Then you set D equals 3, and you do the Fourier transform. And there's 2 singular terms. And you run through this differential regularization that I did before, where you replace 1 over z to the 4th with some derivatives acting on a log. And then you take a scale variation of that, and you find 2 terms, again, that correspond to these leading 2 singularities. And then you compare that with your anomaly action. You can almost do it in your head you need to know how these coefficients vary with respect to the position of the boundary. So if lambda is a function of where you are in the space, then it will vary as you move the boundary around. And so the normal derivative will vary as well, and the extrinsic curvature will vary as well. And you can see you can kind of plug these things back up into the expression above. So like if I plug in the variation of lambda up here, I see I'm going to get 3 normal derivatives out of that, which matches the 3 normal derivatives here in the scale variation of dO. And you can even see the coefficient matching. You have a minus 2 over 4, which is matching the 1/2. And that minus sign is that, whether it's the variation of the distance or the energy scale that you're doing, that switches the sign. And similarly, you can match this term, the k term. So now there's 2 contributions. There's one that comes from varying k, and then there's one that comes from varying n. And actually, since there's 2 n's, that has a weight 2 here. So you have the 2 n's which come with a 2 times a 2. There's an integration by parts when you add it to the other term, which comes with a 1. And so out of this, you get a 3. And indeed, there's a 3/4 there. So you can sort of see it matching up already, at least with a little bit of a cheat sheet to know how things transform. Okay, so that's DO. That wasn't bad. And then what held us up forever and ever and ever, and maybe shouldn't have, was this monster stress tensor marginal operator. And I think the real holdup was that the anomaly is not just coming from a coincident limit or a boundary limit, but you got to somehow do both at the same time. And one crucial insight which Itamar had early in the process, and then there was still a lot of things that had to happen afterwards, was to combine the spatial coordinates and the normal coordinates into a 4-dimensional variable. And then, box of 1 over r squared, that's a 4-dimensional delta function. And for us in this context, that's a delta function that takes you to the boundary and the coincident limit at the same time, which picks out this anomaly that we're interested in. And that wasn't the whole story. There are further boundary terms, and it's quite a mess. But at the end of the day, the dust settles, and you can match the scale variation of this T mu nu O with the anomaly action I wrote down at the beginning. All right. And so that's part 1 of the paper. And then part 2, which I'll be fairly brief about. So this was the case about trying to extend this to a 4-dimensional defect in some larger ambient dimensional conformal field theory. And you start out with the idea that, well, it should involve the Euler density, which is now something quadratic in the curvature. And it should involve this anomaly in the 1-point function, which will now involve 4 normal derivatives of the coupling, not just 2. And somehow if we have to add these 2 things to the anomaly action and make it Wess-Zumino consistent, and adding just these 2 terms is, maybe as you can already see, is not going to be enough. And there's indeed a whole menagerie of other weight 4 terms you can construct out of the Ricci curvature and the extrinsic curvature. And D should be a derivative, so weight 1. And let's write the answer in this funny form here, where I have my Euler density term with my coefficient F and all of these other coefficients tuned appropriately to make things Wess-Zumino consistent, to make the the action of these Weil transformations abelian. And the answer after a rather lengthy computer search is the following. So that the A column is the first column. These are all the terms that are showing up in this Wess-Zumino consistent anomaly. And then the further columns, these are sort of like ambiguities. You could add any of these further 3 columns without affecting Wess-Zumino consistency. They're kind of objects in the kernel of this anomaly action. But the basic object here is sitting in the first column, and all of these weight 4 objects you can see of different kinds, R with 2 derivatives, K with 3 derivatives, so on and so forth. And at the end, it all works out to give the right answer. At least we think so. We did a few checks, not very many. we did that same check I showed you at the beginning, looking at an S4 defect inside a d-dimensional sphere that gives you the right coefficients for the Euler density and the 1-point function, the normal 4 derivative terms for lambda. And you can also look at the scale variation of the displacement operator with the marginal operator, and that gives you, I think, 3 things that you can check. So there's 3 singular terms now in that Fourier transform instead of 2, because there's a higher power of the distance in the denominator. So you get to look at these 3 rather peculiar looking coefficients, combinations of these coefficients, and it works out the way it should. So, I mean, we're reasonably confident that this is an answer. I'm 90% sure there's better ways of writing it down, but that's what we got. So that kind of brings me to the end of my talk. I'll just leave you with some takeaway messages, which is the same takeaway messages I've been hammering at throughout the last hour. One is the central result that this Euler density anomaly coefficient depends on bulk marginal parameters in the following way. You take a derivative of the anomaly coefficient and you get the 1-point function for that marginal operator. We looked at the effect of anomaly action, both in the 2-dimensional and the 4-dimensional cases, and I gave you some reasons to believe that we got the right answer. And so those reasons were some non-trivial checks we did with correlation functions involving the displacement operator and the stress tensor. Okay, so that's the takeaway message of the talk, and I'll say a little bit about further projects. I think there's kind of a moral here about how, if you restrict yourself to the boundary deformations, boundary RG flows, it's fairly restricted, but the bulk somehow allows you access to many different kinds of boundary and defect behavior. I think it's a lesson that we've seen echoed in many other contexts, like when we talk about compactifying d-branes on internal manifolds in string theory to get a plethora of different kinds of field theories. It's a sort of similar kind of behavior where the bulk behavior gives you access to many, many different kinds of boundary behaviors. It's not as restricted. So, I mean, moving forward, I think one project that Itamar and I had in mind was to look at more complicated correlation functions, which aren't completely fixed or are as fixed by conformal symmetry, where there's functions of cross ratios that show up, and see how the anomaly action shows up in there, for example, in 2 stress tensors or 2 conserved currents. And another somewhat pressing question, I think, is there some more rational presentation of this anomaly action in 4 dimensions? Maybe using results from conformal geometry. There's this enormous math literature on things like what are the GJMS invariance or Q curvature. Could some of those techniques shed some light on this this rather messy expression we wrote down for the anomaly action in 4 dimensions? All right, I'll end there. Thanks.
So I'd like to ask a question. So sometimes with these anomaly actions, one can get some additional insight by looking at the special case where the conformal symmetry is spontaneously broken and rewriting it in terms of a dilaton, because then it will become a local action for the dilaton. And in particular, in the Komorgodski-Schwimmer type analysis, that was particularly insightful because the figuring out all the terms that you needed for West-Amino consistency led to some interesting dilaton terms that were present even when the background was turned off. Right, some d phi to the 4th where phi is the dilaton with a coefficient that's like delta A. And so I wondered if you guys had thought about doing something similar for your situation.
I think for this guy, this monster, I'd first like.
Well, not that one. The p = 2, 1.
Yeah, I think for this one, there first needs to be something before that. But the p = 2, 1, yeah, definitely. I think even there, more can be said about what this means geometrically. Is there some simple geometric interpretation of this? And also that, one should integrate it up. One should write it as a function of the dilaton and see what it looks like. I've tried a little bit with that, but so far I don't have anything intelligent to say about it.
Okay, cool. But let's see, the terms in parentheses, which of them are themselves Weyl invariant in that expression, in the action? Or are they all non-Weyl invariant?
I don't think any of them are.
Okay, so you're
None
gonna
of them are
get,
Weyl invariant.
so you're gonna get some interesting terms from all of them.
Yes. Yes. No, the only claim is that this is Wessamino consistent, not that it's Weyl invariant.
Yeah.
No, it's something also that Itamar has tried to do. But so far we don't have anything. No, I mean, this is indeed I think it's an important question.
Can the numbers f be computed, the FIs be computed in any examples using this kind of formalism? I mean, maybe if you add some supersymmetry or something. One of the nice things about A, at least in the supersymmetric context, is that it's computable. So I wonder if similar tricks would let you compute some of the numbers that are appearing here.
Like a maximization, something like this. Yeah.
Yeah, or just generally speaking, there's some kind of relationship between A and more computable Tuft anomalies. Well, that's what leads to A maximization. But I mean, are you saying that like in a super conformal field theory, we should go looking for a trick to compute the FIs, for instance?
I think in any theory with a boundary or defect, these FIs are very important data in the conformal field theory, these one-point functions. I mean, they're in some sense part of the definition of the conformal field theory. I mean, there are many examples where we can compute these perturbatively in free theories, in some supersymmetric theories by localization. Although I should be a little careful about what the context is. I mean, when I say that, I have a very sort of broad context where it's not necessarily just this anomaly context, but also the case of these sphere-free energies I was mentioning before. But there is a rather large context in which we can compute these.
How do you compute OI from the sphere-free energy? Can you say a little bit about that?
I think the example I have in mind is, I have to be a little careful about this because it's, so we did this localization of this supergraphene-like theory a while back. So this was a theory on a half of an S4 with an S3 boundary. So in this case, this is not a case where you're going to get a log in these free energies or a log in these correlation functions, but you'll get nevertheless some interesting sort of constant invariances. Or sphere-free energies, if you will, and I thought.
But you say that you can compute in localization. You can compute them as a function of bulk marginal couplings. Is that what you're saying?
Yeah, we could, for example, compute expectation value of f squared in this theory, which had a free Maxwell field in the bulk and interactions on the boundary.
I see.
So in that case, you could integrate your differential equation for A or for F to get it.
Yes, I believe so. Although I'm not sure we looked at that exact question, but yeah, I think in principle. it gets a bit confusing in that case too, because there's also then some, there is an actual A anomaly in the bulk as well, which we did not compute. So this is, so there's this log contamination from the bulk that you have to be careful to separate. I have to think a little bit about this, but I think in principle, the answer is yes.
All right. Well, if are there any more questions for the speaker? Well, if not, then let's thank the speaker again.
Thanks for the nice talk, Chris.